हेलो स्टूडेंट्स, मोस्ट वेलकम इन मैथ रीथ एकेडमी। तो हम लोग इंटीग्रल कैलकुलस का पेपर पढ़ रहे हैं, जिसमें हम रीमान इंटीग्रेशन से रिलेटेड थ्योरम्स को डिस्कस कर रहे थे। तो आज भी हम थ्योरम्स की बात करेंगे, रिजल्ट्स की बात करेंगे कि कौन कौन सी कंडीशंस हैं जिस पे हमारे पास फंक्शन रीमान इंटीग्रेबल होता है, और अगर फंक्शन रीमान इंटीग्रेबल है तो कौन कौन सी प्रॉपर्टीज रखता है। ओके, तो लेट्स स्टार्ट। So today's theorems on the bounded integrable function. So if the function is bounded integrable, then when it will be Riemann integrable. So let's discuss some theorem. The theorem one, theorem first, theorem first, that every continuous function, every continuous function if function is continuous and defined in a closed interval, that function is definitely bounded. So it is obvious the function is bounded. So if the function is continuous, then it will be Riemann integrable. So every continuous function, continuous function is integrable R, integrable R. Okay. So this is first theorem. So I'm not going to prove this theorem. You just remember the statement of the theorem that if the function is continuous and it is defined in some interval, then definitely will be bounded. Okay. So every continuous function is a integrable R. So if we have a bounded function and then we proved that function is continuous as well, so we can easily say that function is Riemann integrable. Okay. Theorem second, that every bounded monotonic function is integrable R. Integrable R. We know what meaning of monotonic. It is either increasing or decreasing. If function is bounded and it is monotonic, it is increasing or decreasing, then function will be Riemann integrable. Okay. नेक्स्ट थ्योरम की तरफ बढ़ते हैं। थ्योरम नंबर 3, that a bounded function whose discontinuities whose discontinuities discontinuities can be enclosed finite in a finite number of intervals of total length less than epsilon. Epsilon is any arbitrary small number, a small arbitrary chosen positive number is integrable R. in the given interval. So what the theorem is saying, let us see. So if the function is bounded, a bounded function whose discontinuities can be enclosed in a finite number of intervals of total length less than epsilon. Whatever we can choose epsilon, arbitrary very small epsilon chosen positive number, it's said to be integrable r is in a given. So it is saying that if the discontinuities are finite, okay, if the you can say the finite number of points are discontinuities, then you can able to say the function is integrable r, otherwise not. Okay, so if the function is uh, bounded, bounded is obvious, bounded, but it is continuous, but in some finite number of points are discontinuity, showing the discontinuity, then you can say the function is integrable r. So this is meaning actually, because if we have some interval like some region, or you can say some interval which is a positive length, okay, then you can say the function, you can't say about the integrability, or integrable r or not, okay. But if the finite number of points are the discontinuities, showing the discontinuities, then you can easily say that function is, it is bounded, and it will definitely will be uh, integrable r, because we can break the definite integral in that points where the discontinuities are showing. So you can easily get the finite integral for that. Okay, so this is actually theorem. If the function is bounded and have some finite number of discontinuity, then you can say the function is integrable r. Okay, so a bounded function whose discontinuities can be enclosed in a finite number of intervals of total length less than epsilon. Total length less than epsilon means there are 1 point within that interval. A small arbitrary chosen positive number. Whatever you choose the epsilon, the length should be lesser than that epsilon. Then you can say the function is integrable r in the given interval. Okay, you can remember this result. So by this theorem we have a remark. I'm just writing a remark here, that if the function fx if the function fx be bounded, function is bounded and has infinite number of discontinuities in the interval a comma b, and even then the function fx is integrable r. If the points of discontinuities can be enclosed in interval of length is less than epsilon. Okay, so this is the same as the previous result. Okay. Next theorem, theorem number 4. What this theorem is saying, if a function fx is bounded and integrable r in the closed interval a comma b, then modulus of fx is also integrable r in that interval. If a function is integrable, then its mod will be also integrable. Okay. So if a function fx is bounded, wait a second. Okay, so if a function fx is bounded and integrable r, and integrable r in this interval a comma b. Okay, then its definite modulus will also be integrable. Then mod of fx is also integrable r. We just read and remember these all statements for the integration. Okay. So, but converse of the above theorem is not. It means if the modulus of a function is R integrable, it may Riemann integrable, then it is not necessary that function is integrable R. Okay. So let us prove this. So let's remark. So for the for the converse, will have to show a function which is which modulus is R integrable, but the function is not. Okay, we will have to show that one because converse is not true in general. So the converse of the above theorem does not exist. Does not hold true. Okay, so for this we have just take one example showing the so the following example will make clear. Okay, so I'm just taking one example here. So I'm just taking let fx is just equal to 1 when x is irrational. When this x uh, is rational. What happened? When x is rational. Okay, and it is equal to -1 when x is irrational. Okay, so now we have take the modulus of it, so we will get some constant function, and constant function is bounded as well as uh, you can say continuous. So in that case, the function will be integrable r. So from a to b, bar of fx dx will be equal to b minus a, because if you are changing between this, and we get two values. If you are taking the minus of b fx dx, and that will be equal to minus times of b minus a, because one value is positive, one is negative. Okay, so it means though both are not equal, so it's showing it is not integrable. That is not integrable, because एक में पॉजिटिव वैल्यू है और एक में निगेटिव वैल्यू है. ओके, बट इफ यू आर टेकिंग मॉडुलस, तो इन द बोथ केसेस, if we take modulus, this is a to b mod of fx dx, so it will be positive value from a to b mod of fx dx. In both the cases you will get b minus a only, and this showing this showing uh, it is equal, so it's showing it is integrable now. Mod of fx is integrable now. Integrable. Okay, so if function is integrable r, then its modulus will be integrable r. If the function modulus is integrable r, then it is not necessary the function will be integrable r. Okay. Okay, so let's we discuss some more properties of integrable functions. So I'm going to discuss some properties of Riemann integrable functions. So some properties of Riemann integrable function. So if function is Riemann integrable in the closed interval a comma b, then what are the some properties that exist? So I'm just writing the theorem first. Theorem 1 for this, that is your integrability of on a subinterval. So here we are taking the function which is Riemann integrable. So what will be the integrability in the subintervals? If you are taking any subinterval, then function is Riemann integrable or not, we will have to check. So integrability on a subinterval. Okay. So if I'm just taking a function, if fx is bounded and integrable r, and it is integrable r in the closed interval a comma b, then it is integrable r, in a subinterval c comma d, contained in, so any subinterval we are taking in this a comma b, closed interval a comma b, then the function will be integrable in this subinterval of this interval. ओके, तो अगर फंक्शन बड़े इंटरवल में इंटीग्रेबल है, तो उसके जो छोटा इंटरवल होगा जो कि उसके अंदर कंटेन्ड होगा, उसके अंदर भी वो रीमान इंटीग्रेबल होगा. दिस थ्योरम इज इन अदर वर्ड्स यू कैन से, in other words, if fx belonging to the R integrable a comma b, and there is some c comma d is some subinterval of this interval a comma b, then this fx is also belonging to the set of R integrable. R c comma d means the function which collection of all those functions which is R integrable in this interval c comma d. So R a comma b means this is Riemann collection of all Riemann integrable functions. So if any function which is belonging to this interval and any subinterval we are taking c comma d, then the function is definitely Riemann integrable on this interval c comma d as well. Okay. So this is the definition. So we have a remark by this theorem, by this result. So you just remember this result, statement of this result, and you just remember the remark. So B, we can easily prove that, number one, that if fx bounded and integrable R, in this closed interval a comma b, then this is minus of fx is also integrable R in this interval a comma b, and you can easily see this is interval a comma b of minus times of fx dx is just equal to minus times a to b of fx dx. So if function is integrable R, then negative of that function is also integrable R. Second one, that if this fx is bounded and integrable R, in this closed interval a comma b, then if you are changing this limits, the negative will be comes outside. It is minus times of b to a of fx dx. So this property hold for the integrable R functions as well. Next, third remark. Okay. So if this is fx, if fx is bounded, and integrable R, in this interval a comma b, then the function, if you multiply it by some scalar, suppose that some k I multiply in this interval, in this function fx, where k is in constant, where this is k is a constant, it's also integrable R, and this value becomes the k times, it's just equal to k times simply a to b of fx dx. Okay, and number fourth, that is your if fx is bounded and integrable r in this closed interval a comma b, and this fx is greater or equal to 0, where this is x belonging to the closed interval a comma b, then the value of its integration is also positive, a to b, and this fx dx will be gives a greater or equal to 0. It means it also gives a non-negative. If function is non-negative, then value of the integration will be also non-negative. Okay. So this is theorem 1, and based on the theorem 1, we have get some remarks. Okay. So just remember this remark. Now theorem 2. Theorem 2, for this integrability on an interval union. Okay, so इंटरवल यूनियन है, इंटरवल्स का यूनियन लेते हैं तो उसमें इंटीग्रेबिलिटी की हम बात करते हैं. सो इफ if a bounded if a bounded function fx is integrable r in this interval a comma b, then it is also integrable r in this interval a comma c and c comma b, where the c is the point between a and b. C is a point of this interval a comma b, and okay. So what is saying, if there is a function integrable in the closed interval a comma b, and we choose any point between a and b, and we break the interval a to c and c to b, then function is also integrable r in this interval, both the interval a to c and c to b. ये तो हमने पहले देख चुके हैं कि सब इंटरवल में वो क्या होता है, हमारे पास फंक्शन क्या होता है, इंटीग्रेबल आर होता है. तो ये जो भी इंटरवल्स बनेंगे उसमें इंटीग्रेबल आर होगा, और इन दोनों फंक्शंस का जो इंटीग्रेशन का सम होगा वो होल इंटरवल के इंटीग्रेशन के सम के इक्वल होगा. ये भी चीज हमें पता है. एंड दिस वैल्यू ऑफ दिस इंटीग्रेशन will be equal to, this is your a to c of fx dx, and plus this is from c to b of fx dx. Okay, so in other words you can say easily, in other words, if this is fx is belonging to, this is r integrable functions on a comma b, and this is c is any point in this interval a comma b, then then this is fx is also belonging to this r a to c, and this is fx is also belonging to this is r c to b. Okay, and we have also this integration from a to b of fx dx is just equal to the both a to c plus this is c to b of fx. Got it? So this is we also learn for the definite integral as well. So these all the results which we have learned for the definite integrals came from the integrability conditions. Okay. Next result on the sum and difference of two integrable functions. So theorem third, that is your integrability of sum and difference. So if function is integrable over this interval a comma b, if fx is belonging to R integrable in a comma b, and another function which is also integrable in this interval, this is R integrable in this interval a comma b, then first is the sum of these two functions fx plus gx is also R integrable. Okay, and this another one is what, this is fx minus gx is also belonging to this. It means difference and sum both will be the R integrable on this closed interval a comma b. Okay, so hope so these theorems you understood well. Okay, so next results, and in the next lecture I will discuss in detail the fundamental theorem of integral calculus, and also I prove the fundamental theorem of integral calculus, and there are two theorems, and then we have the mean value theorem of integral calculus, Bonnet second mean value theorem, Abel's lemma. So the upcoming lectures is very important and very interesting as well. Okay, so we will meet in the next lecture. Learn mathematics and do by calculations by self, and also start thinking about the theorems and results, how they are coming and how they are just we will able to prove or not, how we will prove these and at these things. Okay, so thank you so much, keep watching and keep learning mathematics with me. Thank you so much.